Good evening. Welcome back to Chapter 3. We're going to talk about air temperature on the essentials of meteorology and invitation to the atmosphere. So let's get right to the actual lesson. All right, so the first thing we're going to talk about is the daily warming and cooling of air near the Earth's surface. Each day is like a tiny season. There is a daily cycle of heating and cooling. You're probably very familiar with this when you're, for example, out and about doing your normal stuff, the errands and basically going from place to place. You probably notice that typically the morning time is the time where it's actually the coolest, and then the afternoon, especially the late afternoon, is a time when it's actually the hottest temperatures. Daytime warming, basically air is a poor conductor, so initial heating only affects air close to the ground. Near the surface, convection begins. Once the surface reaches a certain temperature, you'll get these rising air currents and convection. These rising air bubbles, known as thermals, then help to redistribute the heat in the vertical from the Earth's surface aloft all the way up into the atmosphere, higher up in the atmosphere. Now, just how warm the air becomes depends on several factors. Here are the three main factors that determine how the air becomes, how warm it becomes. The first one being the type of soil, the second one moisture content, and the third vegetation cover. So for example, if we talk about different types of vegetation cover, for example a deciduous forest where we have a lot of foliage, a lot of green leaves as compared to a dry, barren desert out in the desert southwest, that's definitely going to impact how the overlying air, how it warms, how it heats. Moisture content is another factor we must consider. The more moisture there is on the ground, the less the temperature range between morning and afternoon. So that diurnal, we call it a diurnal or daily temperature range, that will basically not be as great when you have a lot of moisture, either on the ground or even in the atmosphere on a real humid day. There's not a large spread between the morning low temperature and the afternoon high temperature, for example. Now, there are some places in the world that do experience extremely high temperatures or hot temperatures. One of these locations is known as Dalal, the city of Dalal in Ethiopia. This is the hottest place on Earth, and look at these numbers. This is quite impressive. The average daily maximum temperature in Dalal, Ethiopia exceeds 100 degrees Fahrenheit every single month of the year, except for December and January, when the average maximum temperature is the average high temperature is lowered to 98 degrees Fahrenheit and 97 degrees Fahrenheit respectively. So this is quite a hot place on Earth. Now, the air temperature at this location also exceeds 120 degrees Fahrenheit at many, many days. Now, we talked about the difference in the soil type. Right here we're talking about a very hot, more desert-like area, and that's why that temperature can rise so high. The air is dry. The heat capacity of air. Air has the ability to heat up and cool down 5 times faster than water. So just keep that in mind. Nighttime cooling. Now, what happens overall? As the sun lowers, as we get towards sunset, and then after sunset, the energy that has been built up during the day at the Earth's ground level generally tends to start being distributed in the form of long-wave radiation from the Earth's surface back into the overlying atmosphere, back into space. And as the sun lowers, its energy is spread over a larger area, which reduces the heat available to warm the ground. So there is a certain point during the daily heating and cooling cycle of the day in which the sun's incoming shortwave radiation temporarily exceeds the outgoing long-wave Earth radiation. Radiational cooling, this typically occurs after sunset, where you have long-wave radiation again being all that heat that was built up during the day. It's actually able to escape back out into space more readily. So radiational cooling results in the ground and air cooling by radiating the infrared, that Earth long-wave radiation. And as the air cools closer to the ground much more rapidly than aloft, let's say higher up, we can get what's known as a radiation inversion. An inversion is simply the opposite of what we normally would expect. An inversion is a time where the temperature actually increases with height in the troposphere. So as the ground rapidly cools, the air next to the ground, or the location next to that ground, cools much more rapidly than the overlying air, since air is a poor conductor, really doesn't distribute temperature very well. What happens is you get what's known as a radiation inversion. All right, and this indicates an area where the temperatures are increasing at a certain level above the ground. Okay. Now, what happens over time is we get cold air near the Earth's surface. We get this strong radiation inversion that occur when the air near the ground is much colder than the air higher up, like I just explained. The air near the ground is cooling more quickly or rapidly than the air aloft, temporarily. The ideal conditions for this radiation inversion to form, or stronger radiational cooling, is typically a windless and long night with clear skies and dry air. That's really what you want ideally, is a nearly calm wind, longer nights, and again, clear skies and dry air. This radiational cooling leads to a lot of fog, especially in the wintertime, where the nights are very long and the days are fairly short. Now, a freeze occurs if the cold occurs over a widespread area for a long enough time to damage certain crops. So just keep that in mind. As that air cools rapidly near the surface, or let's say in valleys where there's a natural dip in the topography of the land, you can actually get damage to certain crops due to freeze conditions. Methods of protecting crops from cold night air. So what do we do when we have a really cold night? We have a freeze night. What can farmers do to protect their crops? Well, the first thing they can do is cover up the crops. They can use heaters, which are known as like orchard heaters, which, for example, if I were to try to protect my citrus crop in Florida, for example, the oranges, what I want to do is try to spray down the oranges, actually. It may be coming up here in the lesson, but I just wanted to mention this. As you spray down the oranges with water, what that does is, in the act of freezing, that releases latent heat. That releases heat to the surrounding air around those oranges as they freeze. So therefore, the temperature of the oranges themselves cannot drop below 32 degrees Fahrenheit or freezing point. Now, just like we talked about Ethiopia, Dalal, Ethiopia being one of the hottest places on Earth, we also would talk about places that have extreme low temperatures. These include, in North America, the Yukon area in North America, and Northwest Canada. Lowest temperatures, the coldest winters in the Northern Hemisphere, are typically found in the interior of Siberia and Greenland because we're far away from the modifying or the warming influence of water. When we go towards the interior of a landmass, a continental area, that's, again, as I mentioned, the dry air can cool off 5 times more quickly than water can. All right? Daily temperature variations. Let's talk about that for a minute. The daily diurnal range of temperature, the difference between the daily maximum or the high temperature and the minimum temperature, the low temperature, that's what the diurnal range of temperature is. If I say diurnal range, for example, today in my location, let's say my low temperature was 72 degrees Fahrenheit and my high temperature was 87 degrees Fahrenheit. So my daily or diurnal range of temperature would be 15 degrees Fahrenheit. The difference, basically, you take your high temperature for the day, subtract it from the low temperature of the day. Conditions that impact the daily range include clear skies. Now, on a clear night, you typically have much more radiational cooling that takes place because the air is dry, there's lower humidity, and typically the air can cool off much more quickly than water. But not only that, but that long wave Earth radiation can more readily escape back out into space. Cloudy skies, on the other hand, generally tend, as that long wave Earth radiation tries to rise up from the Earth's surface, it tends to get retrapped or brought back down to the surface because of the clouds. So that basically results in a warmer night and a cloudy sky night as compared to a clear sky night. The mean, when I say mean, I'm talking about the average daily temperature. That is the average of the highest and lowest temperature in 24 hours. Okay? And then that's provided by weather reports and newspapers, on television, and also on the internet. There's a ton of resources available on the internet to actually calculate the average daily temperature. Now, regional temperature variations. How about a bigger area such as a region? There are certain controls of temperature, and the main factors that cause variations in temperature from one place to another. These include the latitude, all right, and the latitude is just simply the distance north or south of the equator. The latitude lines, we call them parallels of latitude, generally run east to west. Land and water distribution. So for example, the interior of continents, like let's say for the United States we use Nebraska or Missouri or South Dakota. That is towards the center of the continent, of the North American continent, the center of the United States. So generally you're going to have a much greater range in the diurnal range between the low and the high temperature for the most part. You're away from a source of water, so it's going to be drier there. Water distribution. Again, coastal cities tend to have more moderate climates than the cities that are located in the interior or the middle of continents. Ocean currents play a huge role in the weather. Just if you were to take a look at the average weather or climate out on the west coast of the United States versus the average weather or climate on the east coast of the United States, there's a cold California current off the west coast, and then there's a warm Gulf Stream current on the east coast. And that results in a big change in the average temperature variations. And then you have elevation. In general, if you're in a mountainous area, for example, like the Rocky Mountains up near Denver, or higher elevations, even further higher elevations in the Wasatch of Utah, for example, into any of the parts of the Rockies up through Wyoming, you're going to have cooler temperatures if you're at a higher elevation, okay, above sea level. Your temperatures will be warmer as you get closer to sea level. All right, this diagram here, just showing you the placement of this instrument shelter box. So to get accurate readings, it's very essential that meteorologists place the instrumentation at the correct location. In this example, I'm showing you a distance of 5.5 feet. That thermometer is 5.5 feet above the ground. That's very important because as the pavement, if it's a pavement, for example, on asphalt or cement or grass, they're going to heat differently, and some of that incoming solar radiation can be reflected, and if that thermometer is too close to the ground, it's not going to read correctly. I can give you an example of this. We used to take temperature measurements on one of the ships I was on, and the actual area on the ground was actually 120 degrees Fahrenheit. Now, once I moved my sensor, my temperature reader, my instrument, about 6 feet to even like 7 feet above the ground, the temperature dropped drastically. So the placement of instrument shelter boxes is very important in giving accurate temperature readings. On the left here, I'm just showing you how temperature typically will drop or decrease with height in the troposphere, with altitude, okay? The shelter also is used, I do want to mention one more thing, that shelter is used to shade that thermometer from being in direct sunlight. That can also have an impact on causing that thermometer to read too warm. All right, now we're moving on to the daily warming and cooling of air near the surface. So what I'm showing you here on the bottom, on the x-axis here, is the actual times, local times. You'll see the noon time is right in the middle of the x-axis, that bottom axis there. And on the y-axis, I see there's energy rate and there's also the temperature changes, okay? So initially we have you can see the incoming shortwave radiation from the sun from basically sunrise about 6 a.m. to sunset about 6 p.m. in this example. And then you can see the differences in the outgoing Earth energy, the incoming solar energy, the incoming energy equaling the outgoing energy at some point during the day. So you see the differences there, okay? So, for example, between 4 and 6 in the morning, that's typically when we have our coolest temperatures, right around sunrise. And that's mainly because the sun's not out yet. The long wave outgoing Earth energy or radiation is basically exceeding your incoming solar energy. But by noon, the incoming solar energy temporarily exceeds your outgoing Earth energy. And then about 5 o'clock on this, or just after 4 actually on this diagram, you can see the incoming energy is equal to the outgoing energy. All right. After that point, the temperatures will start dropping after sunset due to radiational cooling, where the outgoing Earth energy will once again by sunrise the following day exceed the incoming solar radiation. Look at the temperature difference there in the top part of the diagram. You see how we reach a minimum around sunrise, the lowest temperature reading, and then we reach our high point. Surprisingly, it's not at 12 noon where the sun is the strongest. The highest temperature reading actually occurs a few hours into the mid to late afternoon, the highest temperature. That's because that's the point where there's a little bit of a lag. We call it the thermal or temperature lag, where the incoming solar radiation is temporarily exceeding the outgoing radiation. All right, so now we move on to the next slide, and I'm showing you now an instrument, that same instrument shelter box at nighttime. We've still got to keep that distance of nearly 5.5 feet above the ground, that shelter box, okay? So the outgoing long wave radiation doesn't make that temperature reading read cooler than what it actually is as well, okay? Notice how the temperature changes with height. Sometimes we get temperature to increase with height at night, and again, that's that temperature or that radiation inversion, okay? So again, air near the ground is coolest. Air near the ground is the coolest, okay? All right, now we're looking at the daily warming and cooling air near the surface in a mountainous area where we have higher elevation. You'll notice here we have something known as a thermal belt, which typically occurs on the actual slopes of the hills or mountains themselves. And this is an area, the thermal belt is an area where the temperature is actually above freezing. Everything above the thermal belt is below freezing, and everything basically below and above it is below freezing. So there's your thermal belt in the middle. Generally, we have the coldest temperatures are going to sag because the cold air is more dense. In a mountainous area, your coldest temperatures at night will typically be in the base of that valley there, that lowest point, because air is dense and it wants to go downhill. Right? Just showing you what the thermal belts, or the thermal belts known as. And then this is something known as a, this is a wind machine in an agricultural area. And what that wind circulation does is it tends to keep the air well mixed, so you don't have freezing temperatures. It's another method that farmers use to protect their crops. If you have some kind of circulation of the fan blowing here in this agricultural area, again, it'll result in more mixing, so you don't have very cold temperatures at the surface. It kind of mixes everything out. I did talk about the importance again of, for example, in January we have these really cold shots of air that come down into Florida. Sometimes it goes into California even in some of these orchard areas where you have citrus crops. Generally, the farmers will spray the crops, and basically these crops, you can see in the picture here how the one on the bottom right is completely encased in ice. And what that does, when in the process of freezing, we learned this in the last lesson, freezing tends to release heat to the surrounding air, that immediate surrounding air around the oranges, around grapefruit, and that will help protect that citrus crop from really getting damaged. So surprisingly, spraying with water is a good tactic to use if you want to save some of these citrus crops because of that release of that heat. Right, here is the general, just look at temperature with, on the bottom there you see your temperature degrees in Fahrenheit and degrees Celsius. At the y-axis there on the left and the right you have the altitude. Altitude is in feet on the left and altitude is in meters on the right. This is just showing you how the differences occur throughout the daily temperature, the course of a day with the daily temperature. All right, here's a nice little chart. This is some of the key points of temperatures around the globe. All right, this is a real interesting thing to take a look at. So the average annual temperature, for example, at the South Pole is negative 57 degrees Fahrenheit. The world record for the lowest temperature was negative 129 degrees Fahrenheit down at Vostok Research Station, Antarctica, on July 21st, 1983. Unbelievable. All right. And then the hottest temperature, for example, let's see, I'm looking for it right now. The hottest temperature is Death Valley for North America at 134 degrees Fahrenheit in July of 1913. So again, this is just showing you how the temperature can really swing from super cold to super hot all the way around the globe. All right, now if I were to take a look at the heating and cooling, generally, again, the daily range, how it changes just with altitude. Temperature does change with altitude. This is just showing you that daily range from the maximum on the left, the daily maximum to the daily minimum on the right, and then that mean temperature would be basically in the middle. This is some of the processes that are involved as far as heating and cooling throughout the day. For example, on the left, I'm showing a cooler day diagram. We have a smaller daily temperature range between the morning low temperature and the afternoon high temperature because as the sun's radiation or the shortwave rays come in, they tend to get reflected off the clouds and they get basically redirected back out into space. So clouds act as a shield. They do not allow that shortwave radiation to readily reach the ground, so therefore it remains cooler. At nighttime now, as far as cloud cover goes, the sun's down, that heat's trying to escape from the Earth's surface, but it's having a hard time doing that. So at nighttime, clouds act as a blanket and keep heat trapped closer to the ground. So therefore, clouds during the day result in cooler temperatures, but at night they result in warmer temperatures. Now, what about clear days, clear nights? Clear days, we have a larger daily temperature range because that short wave incoming solar radiation readily reaches the Earth's surface. And then at night, that long wave Earth IR radiation tends to readily escape and go back out into space. So a larger temperature range with clear skies, a smaller daily temperature range with cloudy skies. Now, here's a look overall at the global scale for temperatures. You'll notice there in North America and over the Asian continent, Siberia, look how closely spaced your isotherms or lines of equal temperature are. Each one of these lines represents degrees Celsius for temperature. Notice how closely packed the isotherms or lines of equal temperature are, these lines, over the continents as compared to the water areas. Also, I want you to notice that the overall isotherms are not as packed as tightly over the southern hemisphere, south of the equator. So in the northern hemisphere, we have much more closely, tightly packed isotherms, lines of equal temperature, because we have more continental locations. In the northern hemisphere, north of the equator, we are basically 60% land masses and 40% ocean. The southern hemisphere is the exact opposite, where you have more water, 60% water, 40% land mass, which results in less of a isothermal gradient or temperature difference. Now let's take a look in the summertime. Not only when I talk about isothermal gradients do we talk about continental versus water, but we also need to talk about during the seasons. So for example, this diagram shows you in the summertime what the isothermal gradient is, what that temperature pattern looks like. All right, so in the summertime, in the southern hemisphere, your isotherms, lines of equal temperature, are spaced much further apart. There is less of a temperature gradient during the summertime as compared to the winter. So you notice over North America, over the United States, in the upper left here in this diagram, those isotherms are basically packed. They're much further apart, the spacing of them, indicating a weaker temperature gradient. Now let's take a look at some locations and just compare. We are comparing a continental location on the left of St. Louis, Missouri, and on the right we have more of an ocean area, Ponta Delgada, the Azores. All right, I want you to notice how much sharper that curve is over St. Louis on the left as compared to Ponta Delgada, Azores on the right. Your annual temperature range in St. Louis, for example, between the coldest month and the warmest month, between basically January and July and August, is a whopping 48 degrees Fahrenheit. Whereas the annual temperature range for the Azores, Ponta Delgada over the ocean there, the annual temperature range, the curve is much more gradual, not as steep, and the annual temperature range is only 14 degrees Fahrenheit. So this really gives you a really good idea between the left, a continental location, St. Louis in the middle of the continent, and then Azores, Ponta Delgada in the middle of the Atlantic Ocean, and how the effects of land and water play into the annual temperature range. Here's an example of annual temperature ranges again for San Francisco, California as compared to Richmond, Virginia. Now in this diagram, I want you to pay attention on the left in San Francisco. San Francisco and Richmond, Virginia are at the same latitude, 38 degrees north. But if you notice, the curve is much more steeper between the warmest and the coldest months in Richmond on the right. The reason this is because the ocean currents. San Francisco sits right there on the water on the west coast, where there's a chilly water from the very cold California current produces chilly water right offshore. Water temperatures are generally in the 50s in San Francisco, right offshore. As that wind blows from west to east, we talked about how the weather systems move from west to east. As that wind blows from west to east in the mid latitudes, that tends to basically have the wind blow, bring it over that colder air, or that colder water rather. That wind blows in over the colder water and produces much chillier temperatures in San Francisco. As compared to the right, Richmond, Virginia, we have a warm ocean current on the east coast of the United States known as the Gulf Stream. And a lot of times in the summer we get more of a southeast or south wind that generally blows right in off that warmer ocean current. So it's much hotter in summer in Richmond as compared to San Francisco. Now in wintertime, basically you have Richmond much colder because the air comes more from a continental location, more from Canada, the air masses, as compared to San Francisco, which come in off the Pacific Ocean. All right, so how do we use temperature data? There's a couple terms I want you to be familiar with. The first term is heating degree day. People begin using heat when the temperature typically drops below 65 degrees Fahrenheit. That's usually when we turn on the furnace. It kind of gets chilly in the house. A cooling degree day occurs when people begin to start cooling things using air conditioning when the temperature climbs above 65 degrees Fahrenheit. It starts to get a little bit warmer in the house. So that's a cooling degree day. And then a growing degree day when the average daily temperature is 1 degree above the base temperature for a crop. Okay? So these are three terms I just want you to be familiar with. I want to show you a diagram here. Generally, this shows you, I'm looking at the number, I believe the number of heating degree days. Yes, heating degree days. I got larger numbers up to the north. So look up in northern Minnesota in the wintertime, North Dakota where it's really cold. You got 10,000 heating degree days. As compared, look at the Gulf Coast now. Where you're located, if you live in the Pensacola area or anywhere on the Gulf Coast, you are sitting between 1,500 and 2,000 heating degree days. So basically, your temperatures are not nearly as cold. So this gives energy companies, electrical grids, that type of thing, a great idea of how much energy use is going to be for the heating and the cooling. All right? And this is a heating degree day. The higher numbers are where it's colder up to the north. The lower numbers are towards the south where it's milder. Here's an example now of a cooling degree day. Now you notice how things flip around here, right? So lower values are to the north in the summertime because the temperatures aren't nearly as hot as the south. Florida, South Texas, look at the desert Southwest, 4,000 cooling degree days out towards southern Arizona into southern California in some of those valleys, those desert valleys where it gets really, really hot. Las Vegas, you're up there, but look at to the north, over Maine, over New York State, Massachusetts, only 500 cooling degree days in the summer. So that shows you the big difference between what the demands are for heating and cooling throughout the different seasons. And this shows you estimated growing degree days for certain naturally grown agricultural crops to reach maturity. So your base temperature, for example, for beans on South Carolina is 50 degrees Fahrenheit. The growing degree days to maturity typically takes 1,200 to 1,300 growing degree days. Corn, the sweet corn in Indiana, it's so delicious, believe me. 50 degree base temperature for corn. And you notice every crop is different for a base temperature, or what they use as a base temperature for growing degree days calculations. But look at that, 2,200 to 2,800 growing degree days to maturity for that sweet corn of Indiana. And then peas in Indiana, 40 degrees. So look how the base temperature is much lower for peas. So peas can grow at much colder temperatures is what we're saying. The growing days to maturity is 1,100 to 1,200 for peas. All right, so there are differences in the base temperature for the growing degree days. So you just got to pay attention to the different crops. All right, so we kind of hit this last time. Now we're talking about how the temperature impacts the human body. We did talk about the difference between sensible and latent heat the last lesson. Sensible heat, again, being the heat that we can actually feel. the actual human body's perception of temperature. When you're sitting out in that sun and you feel you're starting to sweat, the sun feels very warm, that's an example of sensible temperature. And it can actually be measured by a thermometer as well. The body stabilizes temperature primarily through metabolism. That's generally the way we do it. The wind chill index, this is an example of how cold the wind makes us feel. We'll be looking at the wind chill index in the wintertime. There's actually wind chill charts that are developed taking into account both the wind and the air temperature. Frostbite is a condition in which your skin freezes. And then hypothermia is a rapid progressive mental and physical collapse that accompanies lowering of human body temperature. We're human beings. We like to have our body temperature at 98.6 degrees Fahrenheit. That's where we should be. So just like anything else, if we get hotter or colder, our body tries to react, and certain things happen through metabolism. For example, we sweat when we're hot, right? We shiver when we're cold. And these are the body's reactions to try to keep our body temperature stable. All right, now we're going to move into an example of a wind chill chart. Okay, so if you look at this, we're showing you wind speed and air temperature in degrees Fahrenheit. And if you have a stronger wind, you're going to have lower temperatures and stronger winds generally yield much lower wind chill values. What it feels like is much colder than the actual temperature. Okay, and on the other hand, we'll show you humidity maybe. I think we're going to show humidity, but we may not. But just keep in mind, again, with wind chill, that the colder the temperatures and the stronger the winds blowing, basically the colder it's going to feel, the lower the wind chill value. So different instruments when we measure air temperature, we're going to talk about that briefly. We're going to talk about the thermometer. There's different types of thermometers. There's a liquid in-glass thermometer. There's a maximum and minimum thermometer, which basically will record your highest and lowest temperatures for the day. A lot of instrumentation today is more digital. There's electrical resistance thermometers, and there's bimetallic thermometers. There's also certain automated systems across the United States, typically located at airports, and these are known as ASOS, A-S-O-S, which stands for the Automated Surface Observing System. This is a suite of instruments that will record your temperatures, your humidity, barometric pressure, your cloud ceiling, where the clouds are at in the sky above the ground, stuff like that. They're very useful instruments. Radiometers, there's thermographs. Thermographs are simply like recordings. Thermographs basically record the daily temperature changes. And then data loggers also keep track and archives of the daily temperature readings. So here's an example of a thermometer. You can see there's a bore. That bore is that little cylindrical tube there in the center. The little black marks on the top are your temperature scale marks. This is a liquid thermometer where you have liquid within the bore. And then there's constriction. There's a little constriction piece there attached to the bulb at the very base of the thermometer. All right, so this is an example of a, looks like a minimum maximum temperature thermometer. You do have liquid in the bulb, which is that small little circular piece at the bottom. You do have the liquid rising up to, in this case, the current temperature of 72 degrees Fahrenheit. You'd read it where the top is located. There's the bore and the meniscus. The meniscus is the point where that liquid tends to dip. You're going to read, the way you properly read that would be the lowest point of that dip, would be the actual temperature. In this case, we're showing you a minimum temperature for the day occurred of 62 degrees Fahrenheit. So there's an index marker in there that keeps track of that stuff, that data. Measuring air temperature, here is the example of the ASOS, the Automated Surface Observing System. I forgot to mention in the bottom left there also has a rain gauge, that tipping bucket rain gauge there. But it also measures wind speed and direction. It has your temperature sensors on it. It also measures visibility, the prevailing visibility in miles, statute miles typically. And also, there's clouds in this picture. There's something known as a ceilometer, which actually will shoot a laser to the sky and actually measures the base of where the clouds are at. It does have limitations, the ASOS on that, however, measuring cloud heights. Right, and then this is a thermograph. This is an example of a thermograph. It's showing you a written log or record of temperature changes on this. This drum rotates. It's like a cylinder. It rotates as this pen of ink, the ink trace occurs. You can basically take this paper off, as it over time it'll record the temperature, and you can actually pull it off and spread it out and actually look at how the temperature's changed over time. It does a continuous trace via that pen, recording of where the temperatures are at throughout the day. So in summary, to wrap things up with this lesson, Chapter 3, there is daily variation in air temperature near Earth's surface. It's controlled mainly by the input of energy from the sun and output of energy from the surface. So you have shortwave radiation coming in from the sun, long wave outgoing radiation from the Earth. All right. The greatest daily variation in air temperature occurs at the Earth's surface. This influences our lives in many ways. For example, what the temperature is, that's one of the first things we look at when we wake up in the morning to decide what we're going to wear for the day. What clothing are we going to wear? What energy use, how much energy use are we going to have? We talked about the heating degree days and the cooling degree days. What's the energy demand, okay, on electrical grid systems? How much AC you're going to use, how much heating you're going to use. And then agricultural planning. Farmers, they're looking at the forecast all the time. Their livelihood depends on the weather. All right, they are certain methods they can use to try to prevent damaging freezes. For example, spraying the oranges if it's a orchard, or using those fans, wind turbines, to circulate the air and result in more mixing, stuff like that. Okay, that wraps up the lesson today. I hope you enjoyed it. Chapter 3. Please let me know if you have any questions along the way. Enjoyed this. Have a great day, everybody, and we'll see you again soon.